Welcome to Engineers Newsletter Live program. I'm Jeannie Harshaw from Trane's System and Application Engineering Group, and today we'll be discussing the selection of chilled water and hot water coils. Today's program is registered with the American Institute of Architects Continuing Education System and qualifies for Health, Safety, and Welfare credit. So AIA members, please provide your member number to your local host before leaving today's session. And credit for attending this program can also be applied toward the LEED Credential Maintenance Program or your Professional Engineer's License. So PEs, please check your state's requirements. To cover the topic today, Trane Applications Engineer John Murphy will be joined by a few guests. Brian Hoffendorfer, an application engineer in our Lexington factory, and Todd Michael, a coil heat transfer engineer here in La Crosse. Now, water coils are fin-tubed heat exchangers consisting of rows of tubes that pass through sheets of formed fins. They're used to transfer energy between two fluids, typically air flowing across the outer surfaces of the fins and tubes and water flowing through the tubes. The construction of the coil impacts the rate of heat transfer, as well as the resistance to air and water flow. With the wide range of air flows, water flows, and temperatures, there's a huge number of possible applications for a water coil. So the coils used in HVAC systems have a wide array of construction and configuration options that alter the coil's ability to transfer heat. The primary characteristics are the face area of the coil, the number of rows and diameter of the tubes, the number of fins and the design of the fin surfaces, the length of each circuit and the number of tubes fed, and whether or not the tubes contain turbulators. In addition, some of the options for construction of the coil include the materials used to make the tubes and the thickness of the tube walls, materials used to make the fins and their thickness, casing material and its thickness, the types of headers used and their material of construction, and coil surface coatings. All of these options help project teams select the optimal coil design for a given project. On today's program, we'll start by discussing the impact of water and air velocity on coil performance and recommended ranges for both. Then we'll walk through some example selections of both chilled water and hot water coils, and finally wrap up with a brief discussion on coil freeze protection. So Brian, why don't you get us started?
Thanks, Jeannie. As air passes through the coil and contacts the tube and fin surfaces, heat transfers from the air to the flowing water through the tubes. The temperatures and flow rates dictate the amount of heat transferred. But as with any fluid movement, there's also resistance to the flow which must be overcome by fans and pumps. The velocity of water through the coil tubes is determined by the geometry of the coil. Contributing attributes include the tube diameter and how the coil is circuited. By varying the number of tubes fed and the cross-sectional area of these tubes, a variety of flow patterns can result. Let's look at some different ways to circuit a water coil. The first diagram is an example of single-row serpentine circuiting, also known as full circuiting. Every tube in the coil row is fed with water in this case. This is the most common circuiting design used and accommodates a wide range of applications. This next diagram shows dual row or double serpentine circuiting. For these coils, 2 rows of coil tubes are fed simultaneously with water. This allows for the same water flow rate to enter the coil supply header, but will effectively reduce the water velocity in the tubes by 50%. This is a great method to reduce the water pressure drop while maintaining the coil capacity and becomes a more common selection, especially with longer cooling coils. As these last two are examples of partial row serpentine circuiting, also known as fractional circuiting. Here you can see that only some of the tubes in the coil row are fed, which allows for increased water velocity. We typically see this design used more for heating coils. Changing the circuiting can drastically change water velocity and the heat transfer characteristics of the coil. Tailoring the coil geometry to achieve a desired water velocity can help minimize the negative impacts of either too high or too low of a velocity. Consequences of too low of water velocity include tube fouling from sediment scaling or microbial growth, air trapped inside the tubes which causes a loss of capacity, noise, or vibration, poor distribution of water in the coil resulting in non-uniform coil face temperatures, and a higher risk for water freezing inside the tubes. On the other hand, too high water velocity can cause the following: erosion of the inside surfaces of the tubes, especially at the U-bends, excessive water pressure drop, and noise. There are also diminishing returns on coil capacity with higher velocities, so the expense of moving the water faster cannot be justified through increased capacity. Design guidelines for water velocity should take into account all of these risks, as well as the specifics of the actual project. One source of guidance on water velocity is AHRI, the trade association that represents global manufacturers of air conditioning, heating, and refrigeration equipment. Most coil manufacturers rate and certify their performance selection programs using AHRI standard 410. This standard establishes a single set of testing and rating requirements for determining capacity, as well as air and water pressure drops for cooling and heating coils. This provides design engineers with an apples-to-apples comparison of coil performance from manufacturer to manufacturer. For cooling coils, AHRI requires selections to have a water velocity between 1 to 8 feet per second. For heating coils, the water velocity must be between 0.5 and 8 feet per second, and the maximum velocity is lowered to 6 feet per second for cooling coils using either ethylene or propylene glycol. Selecting within this range will ensure that the variation between predicted performance and actual performance is minimal. However, it is possible to accurately rate the coil performance above or below these velocities. Another source of recommendations, the ASHRAE Handbook, suggests that the cooling coils are best selected with water velocities between 2 to 4 feet per second. Water pressure drop can often be a defining characteristic of a good or a bad coil selection, so this velocity range should provide a good balance between coil size and minimizing air and water pressure drops, as well as the other risks I mentioned. Heating coils typically require fewer rows of tubes, which allow them to be selected at higher water velocities without resulting in high water pressure drops. So the ASHRAE Handbook recommends 4 to 6 feet per second. Fluid velocity is also important because it is one of the key factors for determining the flow turbulence, along with the fluid density and viscosity and the tube diameter. As the turbulence of a moving fluid increases, so does its ability to transfer heat from the tube wall to the fluid and vice versa. This chart from AHRI 410 depicts the turbulence of the fluid flowing through the coil tubes as described by the Reynolds number on the x-axis, which is the primary driver of the heat transfer coefficient, on the y-axis. The chart plots the Colburn J heat transfer factor versus the Reynolds number and is used by coil manufacturers to rate their selection programs. There are 3 distinct regions of flow turbulence: fully developed flow, also known as turbulent, transitional, and laminar. Reynolds number is used to define these 3 regions. When the Reynolds number is above 10,000, the flow is turbulent. Between 2100 and 10,000, it's considered transitional. And when the Reynolds number is below 2100, the flow is laminar. Right at the point where the flow changes from transitional to laminar is where the heat transfer coefficient bottoms out. As the Reynolds number decreases below this point, the length and diameter of the coil tubes plays an important role in accurately determining heat transfer performance. The HVAC industry has long been aware of the issues and concerns related to laminar flow in coils. But how big of a concern is it? I wanted to bring Todd in on this discussion since he has spent the past 18 years serving on the AHRI 410 Engineering Committee. So Todd, what's the concern about laminar flow?
The typical concern expressed is that coil heat transfer and the accuracy of performance prediction models deteriorates when the Reynolds number falls into the laminar flow region.
So the risk is that coils may not provide as much capacity as was predicted.
Correct. For years, many design engineers have required that coil selections avoid this laminar flow region. But you need to know some history here. As Brian mentioned, AHRI Standard 410 specifies the performance methodology for all coil manufacturers to rate their products. From 1964 to 2001, the coil performance models in this standard were based on the McAdams equation for water film heat transfer coefficients inside smooth tubes, which is accurate in the turbulent region, but begins to lose its accuracy when the Reynolds number drops below 10,000 into the transitional region, and even more so in the laminar region. The industry had long recognized this inaccuracy through field experience, which justified this fear of laminar flow. Since performance prediction models overestimated heat transfer in the laminar and transitional regions, many engineers just simply avoided selecting coils to operate in those regions altogether. However, some coil manufacturers, including Trane, had created and were using more accurate models for water film heat transfer coefficients inside smooth tubes. The AHRI 410 Engineering Committee studied and agreed on this new methodology, which was incorporated in the 2001 edition of AHRI 410. So now, coils can be accurately rated well into the laminar flow region without fear of large discrepancies between predicted and actual performance.
But doesn't the performance of the coil still drop off severely in laminar flow? The chart seems to depict a fairly large reduction in the heat transfer coefficient.
While there is a reduction in performance as the flow turbulence moves from transitional to laminar, it is by no means as severe as the chart seems to suggest. This chart plots coil capacity on the y-axis versus water flow rate on the x-axis. The blue line is a performance model from the 2001 version of AHRI 410. This shows a slight dip in capacity that is less linear than the rest of the coil performance, but it is really not an issue. For comparison, this red line shows the obsolete AHRI model prior to 2001. Again, this demonstrates how the old model overestimated capacity, which caused the unwarranted fear of laminar flow. Laminar flow does not cause a severe drop-off in capacity, and the AHRI prediction methods allow coils to be rated accurately well into the transitional and laminar flow region.
Okay, thanks Todd. Now let's switch from water velocity and discuss air velocity through the coil. The contributing attributes to air velocity are the size, or face area, of the coil and the airflow rate. Just like with water flowing through the coil tubes, care should be taken to avoid an air velocity that is too high or too low. Risks associated with air velocity that is too low include non-uniform coil leaving air temperatures and less accurate prediction of coil capacity. While reducing the air velocity can save fan energy, there are limits which result in diminishing returns. On the other hand, too high of an air velocity can contribute to noise, excessive air pressure drop, and increased risk of moisture carryover. As with the waterside guidelines for air velocity should take into account all of these risks. For certification, AHRI 410 requires cooling coils to have a face velocity between 200 and 800 feet per minute. And heating coils should be selected with an air velocity between 200 and 1500 feet per minute. These ranges are prescribed to provide the most accurate ratings for coils and avoid some of the risks that I've just mentioned. In most applications, the cooling coil also dehumidifies as water vapor in the air condenses on the cold fin surfaces. The water then drains down the coil surface, drops into the drain pan located beneath the coil, and is piped away by the condensate drain line. When a coil dehumidifies, it must be selected to prevent moisture carryover. Too high of a face velocity through a wet coil can result in some of this condensed water blowing off the fin surfaces onto the downstream components in the air handler or duct system. In some cases, moisture carryover can cause damage to the HVAC equipment and contribute to other moisture-related problems in the building. A long-time industry rule of thumb for avoiding moisture carryover has been to select cooling coils for face velocity no greater than 500 feet per minute at design airflow. This has been a fairly reasonable guideline and has seemed to have provided satisfactory results in a broad range of applications over the years. But this is a guideline and doesn't take into account the other factors that affect carryover. Instead, it's a rule born out of what has seemed to work most of the time. If you have no better information to make a decision, then this rule might help you avoid moisture carryover. But it's often too conservative, resulting in oversized equipment, or in some cases, it might not be conservative enough. There are 4 primary factors that contribute to moisture carryover. In addition to the air velocity, the design of the fin surface, the material the fins are made of, and the fin spacing are key factors. And another is the wettability of the fin material. Wettability describes how easily moisture beads up on the fin surface. A simple analogy would be to look at how the paint of a freshly waxed car will bead up water. While this is good for a car, it is much easier for the moving air to strip off the droplets and entrain them into the airstream, causing moisture carryover. Fin material and corrosion coatings are 2 common design features that result in poor fin surface wettability along with dirt or residue on the fins. If you want to learn more about moisture carryover, we've published a white paper that is listed in your biography.
Extensive testing of various fin designs and materials of construction has resulted in a clearer understanding of how these factors affect moisture carryover. This chart depicts the laboratory-tested performance of two coil fin surfaces. The x-axis is fin density, and the y-axis is coil face velocity. The two curves depict the maximum face velocity to prevent moisture carryover for each type of fin surface. First of all, you can see that moisture carryover is more challenging at higher fin densities, where the fins are more closely packed together. So with more fins per inch, you may need to select the coil for a lower coil face velocity. But this chart also demonstrates the impact of the fin surface design. In this case, the fins are made of the same material, but fin design A is engineered to perform at higher coil face velocities without moisture carryover. So what about the industry rule of thumb that Brian mentioned? Here's the arbitrary 500 feet per minute limit. You can see that depending on fin density, both of these heat transfer surfaces are capable of operating at higher coil face velocities. This second chart shows fins of the same design, but demonstrates the impact of materials and corrosion-resistant coatings. You can see that fins constructed of aluminum perform better than copper when it comes to moisture carryover. This is due to the wettability of the fin material. Moisture typically condenses in a film-wise fashion on aluminum fins and in a drop-wise fashion on copper fins. This results in higher wet air pressure drop and lower coil moisture face velocity limits for copper fins compared to aluminum fins. Also, corrosion-resistant coatings typically decrease the wettability of the fin surface, so they require selection at lower coil face velocities. This is due to the reduced wettability of corrosion-resistant coatings, which typically have hard, smooth, glossy surface finishes that result in drop-wise condensation of moisture. Using a trusted coil manufacturer's experience, proven designs, and selection tools, not just rules of thumb, are essential for avoiding moisture carryover.
Thanks, guys. The effects of these design choices and constraints become more apparent when we look at actual coil selections. So next, we'll walk through a few example selections, starting with chilled water coils. Brian?
As I mentioned earlier, in most applications, the cooling coil also dehumidifies as water vapor in the air condenses on the cold fin surfaces. So it must be selected to prevent moisture carryover. As I talked about the industry rule of thumb of 500 feet per minute when sizing the coil. But the face area of the coil dictates the size of the air handler cabinet. The larger the coil, the larger the air handler must be to house it. So the selection of the chilled water coil impacts the cost of installing, operating, and maintaining both the air handling unit and the chilled water system. For instance, the amount of material used to construct the coil determines its initial cost. This is impacted by the face area of the coil, the number of tubes, and the number of fins. A larger face area typically increases the cost of the coil itself. But the size of the coil also dictates the size, weight, and cost of the air handling unit. And a larger air handling unit might require a larger mechanical room, limit access for service, require more structural support, or restrict the arrangement of ductwork and piping. Because the coil is also part of the air distribution system, its geometry contributes to the air pressure drop. A larger air handler will typically result in the lower air pressure drop through its components, which can reduce fan energy. And because the coil is also part of the chilled water system, its geometry contributes to the water pressure drop. A larger coil will typically result in a lower pressure drop. Finally, the extent to which the coil raises the leaving water temperature can dramatically affect both the installed cost of piping and pumping energy. And coil performance can even influence the efficiency of the water chiller. To demonstrate these impacts, let's look at an example coil selection. The condition of air entering the coil is 80 degrees dry bulb and 67 wet bulb. For this example, 8500 CFM of air needs to be cooled and dehumidified to 55 degrees leaving the coil. And for now, we'll assume an entering water temperature of 44 degrees with a 10-degree temperature rise. Let's start by looking at the required capacity.
So here's the condition of the entering air plotted on a psych chart. As this air travels through the cooling coil and is cooled down to 55 degrees, it gets cooled below its dew point. so water vapor condenses out of the air. Therefore, in this case, we do need to be concerned about moisture carryover with this selection. Now let's calculate the required capacity. From the entering and the leaving air conditions, we can determine the corresponding enthalpies. Plugging these values into the total heat equation, 4.5 times the airflow times the change in enthalpy, we calculate the total heat transferred as 329 MBH. This is the total capacity we need to select this coil to produce.
To select the size of this coil, let's start with the traditional sizing convention of 500 feet per minute. The rule of thumb was originally an attempt to strike a balance between an air handler size and energy use, while minimizing the risk of moisture carryover. If we use this rule, divide the airflow of 8,500 CFM by 500 feet per minute. This results in a minimum coil face area of 17 square feet. So we'll select a size 17 air handler, since the unit size typically represents the nominal face area of the cooling coil. But again, there's nothing magic about 500 feet per minute. As I showed earlier, many of today's heat exchanger surfaces have been engineered to prevent moisture carryover at much higher velocities. So here's a traditional selection where we arbitrarily limited coil face velocity to about 500 feet per minute. But what if we selected one size smaller air handler, a size 14 in this case? The size has a face area of just under 14 square feet, so the resulting face velocity is 623 feet per minute. The smaller coil decreases the cost, size, and weight of the air handler, so it requires less floor space and less structural support. But what about moisture carryover?
This chart depicts the laboratory-tested moisture carryover performance of the fin surface design used for this example selection. Like the charts that Todd showed earlier, the x-axis is fin density and the y-axis is face velocity. Again, here's that arbitrary 500 feet per minute limit. You can see that depending on the fin spacing, this fin surface is capable of much higher face velocities. For our example, the size 14 unit has a face velocity of 623 feet per minute. At the selected fin density for this fin design, the maximum is over 700 feet per minute, as depicted by this red curve. So this selection is well below that maximum manufacturer's tested threshold for carryover.
If a goal of the project is to minimize footprint or cost, an overly restrictive limit on coil face velocity can result in the selection of a larger air handler unit than may be necessary. But with today's greater emphasis on reducing energy use, some engineers are specifying air handlers one size larger. A larger air handler will typically result in a lower air pressure drop through its components, which can reduce fan energy. In our same example, a size 21 air handler with more face area results in a face velocity of 408 feet per minute. Of course, this larger coil increases the cost and size of the air handler, but let's see how it affects energy use.
To demonstrate, this slide shows three sizes of cooling coils selected to provide the same 329 MBH of capacity. Starting with the center, with a traditional size 17 air handler, it requires 6 rows with 95 fins per foot. Selecting the smaller size 14 results in a less expensive, lighter unit that takes up less space in the building. But in order to deliver the same capacity, this coil requires more fins. Due to the higher face velocity and more fins, the air pressure drop increases to 1 inch in the smaller unit compared to 0.68 in the size 17 unit. This, of course, impacts fan energy. And pumping this same GPM through a smaller coil does increase the water pressure drop from 8.2 to 11.5 feet. And of course, that impacts pump energy. However, as we just mentioned, if your goal is to reduce energy use, you might want to consider selecting the larger size 21 unit. With more surface area, the coil can deliver the same capacity with only 4 rows of tubes rather than 6. Even though this coil needs more fins, fewer rows and a larger face area results in a much lower air pressure drop, 0.42 inches, and a lower water pressure drop at 5.9 feet. The result is reduced fan and pumping energy. But again, this does increase the size, cost, footprint, and weight of the air handler.
The heat transfer in the coil is driven by the flow rates and differences in temperatures of the air and water, as well as the design of the coil. Choosing various options for the coil size, fins, rows, etc. can often have counteracting effects on the system. For this next example, I'd like to introduce what I call the coil performance triangle. The three sides of this triangle are air pressure drop, water pressure drop, and the physical size of the coil. These three factors are key to designing a well-balanced system that provides the required amount of capacity with the least impact on overall system energy use. In most applications, the design engineer can optimize only two of the three sides of this triangle. That is, if the project requires a traditionally sized air handler and low air pressure drop, then it will come at the expense of higher water pressure drop. Or if I need to minimize both the impact of air and water pressure drops, I likely need to use a larger coil. To further explain this trade-off, let's rerun our previous example for the size 14 air handler. We'll keep the same coil size, but see what happens when we try to minimize either air or water pressure drop.
This first column is the size 14 selection we saw earlier. Keeping the same size coil, we looked at various configurations to see how air and water pressure drop are affected. The center column is an attempt to reduce water pressure drop. Here we change to a dual feed circuiting with 8 rows and 102 fins per foot. You can see that the water pressure drop is much lower, but at the cost of a higher air pressure drop. Then this last column is an attempt to reduce the air pressure drop. Here we change back to single feed circuiting with 6 rows. But now we added these spring wire turbulators inside the tubes, which allowed us to deliver the same capacity with fewer fins. This reduces the air side pressure drop, but now the water pressure drop has gone to the extreme of 26 feet.
These first two examples help demonstrate how air pressure drop, water pressure drop, and coil size are interrelated for a given capacity. Now let's shift gears a little and look into some of the other aspects of coil design. Beyond the size of the coil, when selecting water coils, it is often important to remember that temperatures and flow rates are variables. These should be selected to design an efficient and flexible chilled water distribution system. For years, lots of chilled water systems have often designed for a 44-degree supply and 10-degree temperature rise, or delta T. But designing the system for a larger delta T allows a lower water flow rate to deliver the same cooling capacity, which impacts the cost and energy use of the chilled water system. For this next example, we'll keep the same airflow and air conditions and capacity and evaluate the effect of changing the entering water temperature and delta T.
We'll stay with the traditional 500 feet per minute size 17 unit for this example. The left-hand column is from the first example. It shows the coil selected for 44-degree water and a 10-degree delta T. This next column shows the same size coil, now selected for 44-degree water and a 13-degree delta T. Note that in order to deliver the same capacity, this coil requires more fins, that is, more surface area. This increases both the air pressure drop and the cost of that coil. But the big impact is a much lower water pressure drop and a lower water flow rate. This allows the pipes, pumps, and valves to be smaller and results in less pumping energy. Now let's take it a step further and ask what's so special about 44-degree supply water. This next selection shows the same size coil but using 42-degree supply water and a 13-degree delta T. With the colder water, this coil is able to provide the same capacity at basically no change in air pressure drop or cost. And it still benefits from the lower flow rate and water pressure drop. And this last selection takes it even one step further, with 40-degree supply water and a 16-degree delta T. In this case, the coil provides the needed capacity with only 4 rows, which significantly reduces the air pressure drop and cost. And the larger delta T means an even further reduction in water flow rate. So designing the chilled water system for a larger delta T can allow the pipes, pumps, and valves to be smaller, reducing system installed cost. In addition, a lower water flow rate and pressure drop results in less pumping energy.
Of course, if the chiller is producing colder water, it will use more power. But in many applications, the overall energy used by the chiller plus pumps will be less. That's why many in the industry, including ASHRAE's Green Guide, recommend designing chilled water systems for lower flow rates or larger delta Ts. We've listed several resources on low flow designs in the bibliography in your handouts. And this low flow design concept can also be used on the air side, particularly with cold air VAV systems. We've discussed this concept of colder air on several previous ENLs, which we've also listed in the bibliography.
Thanks, Brian. Next, the guys are going to discuss some of the same choices you have when selecting hot water coils. Todd, you're up.
Just like we discussed with chilled water coils, it is important to remember that hot water temperatures and flow rates are variables. They should be selected to design an efficient and flexible hot water distribution system. For many years, hot water heating systems have often been designed for 180 degree supply with either a 20 or 30 degree delta T. But designing the system for a larger delta T allows a lower water flow rate to deliver the same heating capacity, which impacts the cost and energy use of the hot water system.
To demonstrate, this slide shows an example of the same size coil selected to heat 5,000 CFM of air from 60 to 104 degrees. This requires about 239 MBH capacity. The coil is selected using 180 degree supply water, but with different delta T's, 20, 30, or 40 degrees. Now note that in order to deliver the same capacity, when the coil is selected for a larger delta T, it does require more fins. This increases both the air pressure drop and the cost of the coil. As you can see, both these impacts are pretty minimal for this example. However, the big impact is that a larger delta T allows for a much lower water flow rate and a lower water pressure drop.
So designing the hot water system for a larger delta T results in a small increase in both the cost of the coil and its air pressure drop. But it results in a significant reduction in the water flow rate and water pressure drop. A lower flow rate can allow the pipes, pumps, and valves to be smaller, reducing system installed cost. In addition, a lower flow rate and pressure drop result in less pumping energy. Now, let's take it a step further and ask, what's so special about 180 degree supply water?
Going back to our same example, this first selection on this slide is the same as we saw before, 180 degree supply water with a 20 degree delta T. But these other two selections show the same size coil with 150 degree supply water and either a 30 or a 40 degree delta T. Note that in order to deliver the same capacity, when the coil is selected for a lower supply temperature, it requires more coil rows. Again, this increases the pressure drop and the cost of this coil. As you can see, adding rows had more of an impact than adding fins. But again, the big impact is a much lower water flow rate and a lower water pressure drop. There's another benefit here. A boiler is more efficient when it's making the lower supply water temperature. So why has 180 degrees been such a common design choice for so long? It has to do with the return water temperature. A lower supply temperature means a lower return water temperature. In this example, with 150 degree supply, the temperature of the water returning to the boiler is either 120 or 110 degrees. These temperatures are lower than what's allowed for a conventional boiler, but these temperatures are well suited for the newer condensing type boilers.
A conventional non-condensing boiler is designed to operate without condensing the flue gases inside the boiler. That is, only the sensible heat value of the fuel is used to heat the hot water. All the latent heat is lost up the exhaust stack. This avoids corrosion of cast iron or steel parts inside the heat exchanger. Hot water systems that use non-condensing boilers are often designed and operated to ensure that the return water temperature is no lower than 140 degrees in order to prevent this condensing. However, newer condensing boilers are becoming more popular because of their higher efficiency. Condensing of the flue gases uses more of the energy in the natural gas to heat the hot water, so less of that energy is lost up the exhaust stack. Since condensing does not need to be avoided, this allows for a lower return water temperature, much lower than this 140 degree limit. In fact, a condensing boiler gets more efficient at cooler return water temperatures. This chart is from the ASHRAE handbook. It shows the typical efficiency of a condensing boiler on the y-axis compared to the temperature of the water returning to the boiler on the x-axis. As I mentioned, non-condensing boilers require this return water temperature to be 140 degrees or higher to prevent condensing of the flue gas. But notice how the efficiency of a condensing boiler increases significantly with a cooler return water temperature. So reducing the supply water temperature and designing the system for a larger delta T to lower the return temperature both help to maximize the efficiency of this technology. Moving on, let's look at another common application of hot water coils, which is for reheat and VAV terminals. As I mentioned, lots of systems are currently designed for 180 degree supply. So how does this supply temperature impact the hot water coils in this application?
This slide shows an example of the same VAV terminal unit with heating coils selected to deliver 22.8 MBH capacity using either 180 or 150 degree water. Now note that in order to deliver the same capacity, the coil selected for 150 degree supply water requires more than one row of tubes. Obviously this increases the cost of the VAV terminal. However, using a lower supply temperature results in a lower return water temperature. In this example, with 150 degree supply, the temperature of the water returning to the boiler drops to 116 degrees when a 2-row coil is used, or 106 with a 3-row coil. As you mentioned, this is likely too low for a conventional boiler, but it's great for increasing the efficiency of a condensing boiler. In addition, the multiple row coils allow for different circuiting, which results in a lower water pressure drop. Of course, a drawback of more rows is an increase in air pressure drop. 0.45 inches for the 1-row coil versus 0.79 inches for a 2-row coil. Of course, this impacts fan energy use. But remember that this air pressure drop decreases exponentially as airflow is reduced at part load. The air pressure drop across the coil drops by roughly the square of the reduction in airflow. So when the VAV terminal reduces airflow to about 60% of design flow, the pressure drop is only about 1/3 of what it was at 100% airflow. So because pressure drop decreases exponentially at part load, the actual impact on annual fan energy is not as great as you might think.
Another benefit of using additional rows in VAV box coils is that it makes them better suited for heat recovery. While these coils are often referred to as reheat coils, I think it is helpful to recognize that they have two functions. During cold weather, the heat lost through the building envelope and glass can exceed the heat gained inside from people, lights, and equipment. Under these conditions, the zone has a net heating load, so the air must be supplied at a temperature warmer than the desired zone set point. In this mode, the coil is truly functioning as a heating coil, and this is the mode we often consider when selecting these coils. However, for much of the year, the internal heat gains exceed the heat loss through the envelope. In this case, the zone still has a net cooling load, so the air must be supplied at a temperature cooler than the zone set point. But if this net cooling load is fairly small and the VAV damper has been modulated down to its minimum set point, this coil is used to reheat the cool primary air just enough to avoid overcooling the zone. In this mode, this coil is functioning as a reheat coil. This reheat load is highest when the net cooling load in the zone is 0. That is, the heat loss through the envelope balances with the heat gained internally. As depicted on the right, at this condition, the air is reheated from 55 to 75 degrees for this example. Compare that to the same unit operating in the heating mode shown on the left. Here, the air is heated to a temperature warmer than the zone, 90 degrees in this example. The reason it is helpful to differentiate these two modes is that both the coil capacity and the leaving air temperature required for reheating are significantly less than what's required at the design heating load. In this example, the worst case reheat load is 13 MBH with 75 degree air. Compare that to 23 MBH and 90 degree air for design heating load. Oftentimes, these reheat loads can be met with a lower hot water temperature, making it an ideal application for heat recovery from a water chiller.
This slide builds on the previous example, showing a VAV terminal selected to deliver 2000 CFM at cooling design conditions with a minimum airflow setting of 600 CFM. This top section for heating mode you've seen before, but the bottom section now shows operation in the reheat mode. As Todd explained, at worst case, this coil needs to reheat the 600 CFM of primary air from 55 to 75 degrees, which requires about 13 MBH of capacity. By equipping the VV box with a multiple roll coil, it can provide this capacity with lower temperature water, even down to 105 degrees as shown in this example. This would allow the use of almost any chiller to recover heat from. At design conditions, in the middle of the winter, this chiller is most likely turned off. So in this mode, the heat is provided by a boiler. But reheat may be needed at times when the chiller is operating. So in this mode, you could make use of chiller heat recovery. Both the flow rates and water pressure drops are certainly impacted by the additional rows and the lower supply water temperature. So there's a little balance to be done in the design to ensure that the energy benefit of the condensing boiler and the chiller heat recovery outweigh any impact on fan and pumping energy.
With greater focus on reducing building energy use, condensing boilers, heat recovery chillers, and even geothermal can all benefit from lower hot water temperatures and larger delta T's. Again, while today's E&L focuses on the water coils, we've listed several resources related to these subjects in the bibliography.
Thanks, Todd. Before we wrap up, since the focus of the CNL is on water coils, we want to briefly address the issue of freeze protection. Todd?
If subfreezing air moves through a coil, the water inside the tubes can freeze and cause damage. Typically, a low-limit freeze stat is installed on the upstream face of the water coil. If the temperature of the air entering any section of the coil approaches 32 degrees, the unit controller responds by stopping the supply fan, closing the outdoor air damper, or both. Of course, this adversely affects occupant comfort and indoor air quality. So if a water coil is likely to be exposed to air that is colder than 32 degrees, the system should include some method to protect it from freezing. One approach is to drain chilled water coils during cold weather. This requires vent and drain connections on every coil and shutoff valves to isolate it from the rest of the system. The advantage of this approach is that it has minimal impact on the cost of the air handling unit and has no impact on energy use. However, it does increase maintenance, especially in locations where the temperature can fluctuate widely during seasonal transitions, possibly requiring the coils to be drained and filled several times.
In climates where freezing weather is not as common, some engineers design in a bypass pipe with a small circulating pump and a check valve. This pump operates whenever the outdoor temperature drops below a certain threshold, say 35 degrees. This increases the water flow rate through the coil, which can delay but not prevent the process of water freezing. In some applications, in some climates, this may be sufficient. But be careful not to trust the old adage that moving water doesn't freeze. I live in Wisconsin next to the mighty Mississippi River. It freezes over every winter, and I guarantee you that it didn't stop moving. When the temperature of the inside surface of the tubes drops below 32 degrees, the water molecules that are in contact with the tube walls begin to freeze from the outside in. Pumping the coil to increase the flow rate will slow this process down and possibly delay bursting a tube, giving it time for the air to warm back up again.
A more popular approach is to add antifreeze, such as glycol. This lowers the temperature at which the solution will freeze. The advantage of this approach is that it's predictable and relatively easy to maintain. However, antifreeze degrades the heat transfer performance of coils and chillers, often increasing their size and cost. And it increases the fluid pressure drop, which impacts pump energy use. So it's wise to not use a higher concentration of glycol than is necessary.
Freeze protection indicates the concentration of glycol to prevent ice crystals from forming. And burst protection indicates a concentration to prevent damage to equipment, such as coil tubes bursting. You can see that at a given temperature, burst protection requires a lesser concentration of glycol, which means less impact on heat transfer. For most systems, since the cooling coil is not used during sub-freezing weather, this lesser concentration providing burst protection is usually sufficient for the chilled water system. On the other hand, in a hot water system, a concentration sufficient for freeze protection is more likely needed since it operates in sub-freezing weather.
The next option is to preheat the air before it passes through the water coil. This might involve an electric heater, a hot water or steam coil, or even air-to-air energy recovery device, such as a wheel. The advantage of this approach is that it's predictable and effective. And in cold climates, a source of heat may already be needed in the centralized air handling system. Otherwise, the approach may increase the size and cost of the air handler. In a mixed air unit, Air-Mixing Baffles improve the blending of sub-freezing outdoor air with the warmer return air. This thermal image shows the very cold outdoor air entering the mixing box at the left end of the unit. The blender mixes these two air streams, minimizing temperature stratification of the air before it enters the downstream water coils, so the risk of freezing and nuisance freeze-stat alarms are reduced. The advantage of this approach is that it works consistently and requires no maintenance. However, it does increase the cost and length of the air handler unit. And the baffles add air pressure drop, which impacts fan energy. The next approach is to introduce the cold outdoor air downstream of the cooling coil.
This configuration uses a combination of two different size modules, so that the outdoor air is introduced downstream of the chilled water coil whenever it's colder than 32 degrees. This smaller air path might include a preheat coil, but it can't avoid the risk of freezing this chilled water coil.
These are probably the most common methods used, but there are certainly others. Each method of freeze protection has its advantages and drawbacks, so choose the method that best suits your application. Most of the time when we think about water coils freezing, we think about cold weather. So we don't have to worry about freezing an inactive water coil during warm weather, correct? Wrong. Water coils do not discriminate when it comes to the source of sub-freezing air. When a DX cooling coil is located upstream of a water coil, it can sometimes produce sub-freezing air that can cause the downstream water coil to freeze. Typically, the air temperature leaving a DX coil is 55 to 60 degrees. So what can cause it to produce sub-freezing air? Maybe low airflow through the coil due to clogged filters or a variable frequency drive that's turned down too low. Or even no airflow, which can happen if the compressor is turned on without proof of airflow by the fan. Possibly a poor split system combination that can result in too low of a saturated suction temperature. Or a mixed air temperature that is too low. This can happen with integrated airside economizer control or in a process cooling application. For this situation, always protect a water coil located downstream of a DX coil with a freeze stat, or use antifreeze at a concentration sufficient for freeze protection.
Thank you, guys. Today we talked about several aspects related to the selection of water coils for cooling or heating. As we mentioned, there are a number of publications available that provide more information on the material today, all included in your handout. Additionally, all past broadcasts are available on DVD at train.com/ENL. All are accredited for continuing education, and many are available on demand free of charge. Visit train.com/continuing education for a complete list to satisfy credentialing requirements, and many are lead specific. And remember to fill out a survey and let us know how we're doing. AAA members, turn in your member information to your local site coordinator. And finally, please ask your local host about details for the remaining Engineers Newsletter Live programs this year. There's another Fundamentals ENL on how to evaluate sound data. And then we'll return in fall to discuss small chilled water systems. So please plan to join us. Thanks for your time today. We look forward to seeing you.